Hello, so in this video we will talk about the statement and proof of the Pick's theorem. So before that we need to define a simple polygon. A simple polygon is a polygon whose non-consecutive sides do not intersect. So straightforward enough. So the Pick's theorem says that if a simple polygon has its vertices on lattice points, what are lattice points? Lattice points are those points whose coordinates are integers. Okay, integers. So if a simple polygon P has its vertices on lattice points, then its area is given by area of P is I of P plus half times B of P minus 1, where I of P is number of interior points and B of P is number of boundary points. So if this is the case, then the area can be given by this formula, half times B of P plus I of P minus 1. Okay, now let's see whether this has any authenticity or not. So let's say we have a grid like this, and we have a polynomial which happens to be a triangle. In this case is this. Okay, so what is the width? 1 2 3. And what is the height? 1 2 3. So what should be the area? Area should be half times 3 times 3, which is 4.5 square units. Now let's calculate the area through the formula. So I of P is, how many points are inside? Only 1 point. B of P, how many points? 1 2 3 4 5 6 7 8 9. 9 points. So 1 plus 9 over 2 minus 1. So 1 and 1 cancel out. So we get 4.5 square units here. So this means that this formula, this Pick's theorem, has some validity. So let's now go to the formal proof. For the formal proof, we need two lemmas. Okay. So the first lemma is that every simple polygon has an interior diagonal. Okay. So this is I'm writing it without a proof, but this is simple enough to appreciate that if you have a polygon, then you can have an interior diagonal here. Although the formal proof is not very straightforward, so we leave it for some other time. Lemma 2, which we will be using, is saying that if a simple polygon P is split into polygons P1 and P2, and Pick's theorem is valid for P1 and P2, then it is valid for P. Okay. The same thing can be said as that if the Pick's theorem is valid for P and P1, then valid for P2. Okay, and same with if P and P2, then valid for P1. Okay, so let's move forward and see whether this is actually true or not, because we are going to prove our Pick's theorem through mathematical induction, then we have to use this additive lemma. So let's see. Let's say that we have area of P1. This is given by I of P1 plus half B of P1 minus 1, and area of P2. This is given by I of P2 plus half B of P2 minus 1. Okay. So now we say let the interior diagonal has k points. Okay, so then I of p is what? So I of p is all the points interior to p1 plus all the points interior to p2 plus all the points on the diagonal. Okay, now note that when we have, let the interior diagonal has k points, we are saying excluding vertices. Okay, okay, so we have all the points interior to p1 plus all the points interior to p2 plus the points in the diagonal. What is b of p? So b of p is all the points on the boundary of p1 plus all the points on the boundary of p2, but then boundary of p1 also has k points, right? So then, sorry, also has k points, so we have to take care of that k, so we have to subtract that. Then all the points on the boundary of p2 also have k points, but we have two vertices points as well. So what we'll do, we'll take -1 here and then -1 here. Okay, to see this, let's say we have a rectangle like this and our diagonal is actually here, so k is equal to 0 here. So what is, so this is my p1, this is my p2, and this whole rectangle is my p. So what is b of p1? 1 2 3 4 5 6. And what is b of p2? Again 1 2 3 4 5 6. And what is b of p? 1 2 3 4 5 6 7 8 9 10. Now note that this point and this point was both on the boundary of p1 and p2, so that is why we have to take -1 here and -1 here. So if now I write it like this, b of p1 plus b of p2 minus 2k minus 2. Okay, now let's say area of p1 plus area of p2 is what? This is equal to I of p1 plus half b of p1 minus 1 plus I of p2 plus half b of p2 minus 1. Now what I can do is I can add k here and subtract minus half 2k here. Okay, and then I can subtract 2 here and add 2 here. Okay, now what is this guy? This guy is I of p. Okay, what is this guy? So let me write it. So this guy is half times b of p1 plus b of p2 minus 2k. I should actually say minus half times 2 and plus 1 here. So I can say minus 2k minus 2 and this is -1, -1 and +1. So this is -1. So what is this guy? This is I of p. What is this guy? This is b of p divided by 2, and this is just -1. So we end up with I of p plus b of p over 2 -1, which is equal to area of polynomial p. So this means that this lemma is valid. Now let's go back to our Pick's theorem and start using mathematical induction to prove it. Okay. So now we go here. So we have base step. Base step is n is equal to 3. What is n? N is number of sides or vertices. Okay. So for n is equal to 3, we have to prove it for rectangle. Okay, because we are going to use the additive lemma for this as well. Okay, so now let's say we have a rectangle like this. Now I'm drawing it 5 columns and 4 rows, but this is valid for any dimensions. So let's say this is my W and this is my H. So my question is, what is B of P? How many points are there in my width from in the bottom part? I have W plus 1. And similarly, I have on the top side, I have W plus 1. Correct? Okay, how many on the sides, left and right sides? So this is H minus 1 plus H minus 1. Note that these are the points why we have to be careful about why this is H minus 1 here, because these are already taken care of by the W side, so we cannot repeat it. Okay, now what is I of P? Okay, so what is I of P? Now I of P is, let's say, rows here. How many rows we have? We have H minus 1 rows. And for each row, how many points we have? We have W minus 1 points. So this is my I of P. Okay, now let's say, what is I of P plus B of P over 2 minus 1. So I of P is HW minus W minus H plus 1 plus B of P over 2 is what? We have 2W, 2, so this one goes with this one goes with this one. So then I'll say BP over 2 will be plus W plus H and then minus 1 here. Okay. Now this W goes with this H goes with this one goes with this, and we are left with height times width. So this works with the rectangle. Okay, now we go to our actual base step. Okay. So now a base step is, we have to split it into two cases. One is that we have a triangle like this. Okay, so case 1 is that we have the legs are parallel to coordinate axis. Okay, in this case, you can appreciate that we can make a rectangle like this. So this will become our P1. This will become our P2, and this rectangle is our P here. Okay. Now by our lemma, we can say area of P, this is equal to area of P1 plus area of P2. Okay. Now area of P1 and area of P2 are equal, no? because they are split in exactly that fashion. So we can say area of P1 is equal to area of P. Okay. Now note that for this one, the Pick's theorem holds. So if for this one Pick's theorem hold, then by additive lemma, for P1 it holds and for P2 it holds, or for P1 it holds and for P1 it holds. So we can say P1 it holds and for P1 it holds. So now note the sentence here. For P1 it holds and for P1 it holds. This means for P1 Pick's theorem holds. Okay. Now let's consider another case. Another case is that we have a triangle which looks like maybe like this. Okay. In this case, what we can do is we can make it like this, we can make it like this, we can make it like this. So this one becomes my P1, this becomes my P2, this becomes my P3, and this becomes my P4, and my rectangle becomes my P. Now for P, Pick's theorem holds. For P1, this holds. Why? Because P1 is a right triangle, and we have already seen that right triangle, not for the right triangle, the triangle whose legs are parallel to the coordinate axis, Pick's theorem holds. So P2 also same thing, P3 also same thing. Now you can appreciate that area of P4, this is equal to area of P minus area of P1 minus area of P2 minus area of P3. So for all this, Pick's theorem holds, and from that lemma we can appreciate that for P4. So for P4, Pick's theorem holds. Okay. Now you can play with several kinds of triangles, and you can see that for each triangle, if we embed it in the smallest possible rectangle, we can always find some right triangles, and in some cases you may have one more rectangle. So let's consider that case quickly here. So we have to be careful here. Okay, so we have a triangle, funny triangle like that. Okay, now we have a right triangle like this, right triangle like this. So we have this. So this is a square, and a square is a rectangle, and then we have three right triangles, and then this shaded part. And again you can use the same lemma to prove that this Pick's theorem holds for this triangle. Okay, now we have proved our basis step. Now let's go to the inductive step. So inductive step is straightforward. Inductive step uses lemma 1. So we say that, we write suggest some sentences here. We say since every polygon has an interior diagonal, then we can split a polygon of side of k plus 1 sides into two polygons with lesser sides. And what does induction says? Induction says that in the inductive step, we assume that everything before k plus 1, the Fick's theorem is valid. This is called strong induction, where we just not focus our attention to k, but every integer from 3 to k. So since Fick's theorem holds for the two smaller polygons, it holds for P due to lemma 2. Okay. So then this is straightforward proof for the inductive part. So now you have actually you can draw many pictures here. So you can draw a funny picture like this. So you can draw something like this, 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 and like this. So then you can easily calculate the area of this picture using the Fick's theorem. Okay. Although you can also do it by dividing into squares and triangles, but you can also use the Fick's theorem here. Okay. So this is about this is the video about Fick's theorem and its statement and proof and using strong mathematical induction. Hope it was easily understood and it was clear enough, and thanks for watching. Hope you liked the video.